Alright guys, this is our second problem that we had on exam 1, and on this one we had a relative motion problem. So we had two cars. They were originally driving side by side on this portion of the road right here, and then car A is going to go ahead and go straight. Car B is going to go on this little exit ramp here, which, if you look, is curved. Alright, and the speed of car A was 70 miles per hour. B had a speed of 50 miles per hour. And once B exits the road, there's a 30-degree angle there. Now we're also told that B is going to decrease the speed at a rate of 1,400 miles per hour squared, and then A is going to be increasing its speed at a rate of 800 miles per hour squared. What we want to do is find the acceleration of B with respect to A. All right, so basically that would be like having an observer in A right here, looking at B, and then, what does that acceleration of car B appear to be to the observer in A. We're also told, finally, that our radius of curvature is 0.7 miles. So basically, if we did that, we would have 0.7 miles. Okay, so let's go ahead and get started. And by the way, we want to find the magnitude of the acceleration of B relative to A, and we're also going to find the direction to the angle. All right, so first thing we want to do, let's write out our equation that we need for this. So remember, the variable on top is the one that's going to go on the left. So we have AB equals AA plus AB relative to A. So this is our equation. This is what I'm going to find. And then once I get the vector form, I can go ahead and find the magnitude and the direction. In order to get this, though, I need to find AB and AA. So let's start with AB first because it is the more complicated one. All right, so B is the car that's on this curved path. Okay, so keep that in mind. Let's go ahead and draw a drawing here of the accelerations for AB, for car B. Okay, so remember on this relative motion stuff, I said to just go ahead and use your regular XY coordinate frame. So there we have that. And then now let's label the accelerations. Well, we're told that B has a speed that's decreasing at 400 miles per hour squared. All right, so if your speed is changing by a certain rate, that is your tangential component of acceleration for that object. Okay, so that means the tangential component of the acceleration of B is going to be in the negative direction. So if the motion of B is going this way, like what we see here, that means the acceleration is going to be going, in the opposite direction. All right, so this will be our AB tangential. Okay, and I'll label angles in just a second. So we've got this because, again, it's decreasing, so it's in the opposite direction of the motion for car B, and then it's on a curved path. So what else do I need in here? Well, I need my normal component of acceleration, right? And the normal component of acceleration just comes about from the curvature of the road. So that one is going to be directed in toward the center of curvature, and let's call that ABN. And then now we need to label our angles. So we have this 30-degree angle right here. So if we have that, then that is going to make this 30 and that one 30. All right. And by the way, if you ever get stuck figuring out what angle goes where, the way that I always do that is I draw the regular coordinate system and then I draw the one at the angle shown. So this one here would be 30, which means that's 30, that's 30, and that's 30. So then you just line up what you have here. So this on my diagram is the tangential, this is the normal. All right, so that's how I know that this angle right here is 30 and that's 30. All right, y'all probably hear my dog barking. I'm not sure what she's barking at, but she's upset about something. Okay, so now that we have this, let's go ahead and find the two components in the Cartesian system. All right, so let's find ABT first. All right, so let's go ahead and find ABT, like I said. And if we do that, this is going to be a vector, so put the bar up here. We are going to have negative 1400 because that was the magnitude of that acceleration. It's negative because it's going to the left, and we're going to have sine 30. All right, so that's the I component of ABT. Now it also has a J component, right here. So let's find that. This is the adjacent side to that angle. It's going down, so we're going to have a negative 1400 cosine 30 J. All right, and then now let's simplify that. So that gives us negative 700I minus 1212.44 J. And that's going to be in miles per hour squared. Okay, so now we got this one done, but the acceleration of B has the two separate components, right? Got tangential and normal. So now we need to worry about ABN. So let's do that. All right, this is going to be a vector, so put your bar up there. Now the magnitude of this acceleration is going to be your V squared over rho. All right, so I'm going to put VB squared over rho. And then I need to find my unit vector, essentially. All right, so this one has a positive x component, which would be right here. All right, so that would be cosine 30. And then it's got a negative y component right here, which will be negative sine 30 J. All right, so now we have that. Now I know what VB is. It was given in the problem. I also know what rho is, so we can plug those values in. So VB was 50 miles per hour. So we're going to square that, put it over rho, which was 0.7. And then again, just multiply by this unit vector. So the cosine 30 I minus sine 30 J. And that simplifies out to be 3092.95 I minus 1785.71 J. And again, that's miles per hour squared. Okay, so these are our two components that make up the acceleration of B. So let's put it together. So AB is going to be the tangential component plus the normal component. So essentially what we need to do now is take the like components and add them up. So I'm going to have the negative 700I. I'm going to add that to this 3092.95I. All right, so then we do that. We'll subtract that 700. It's going to be our I component, and then we do the same thing for the J components. I'm going to have the negative 1212.44 minus the 1785.71. And that gives me the J. And then go ahead and simplify, so you get 2392.95 I minus 2998.15 J. That's miles per hour squared. So we did all of this stuff just to find AB. All right, so this is our AB. Okay, so we'll need that. And now we have to find A for car A. All right, so the acceleration for car A. And that's going to be pretty easy. So car A is going in straight line motion, right? It's just going in that Y direction. And we're told that it's increasing its speed, and that rate is 800 miles per hour squared. So that means the acceleration of A in vector form is just going to basically be 800 J. All right, and that's miles per hour squared. Okay, so this one's a lot easier because we don't have to worry about the normal components and all of that stuff. We're not on a curved path or anything like that. So now we can go ahead and go back to this equation right here, plug everything in. Okay, so acceleration of B goes on the left. So we're going to have 2392.95 I minus 2998.15 J. We're going to set that equal to 800j plus acceleration of b relative to a. And now we just solve for that relative term. Okay, so we're going to group up the like terms, and that's going to give us 2392.95i, and then minus 3798.15j. All right, that's miles per hour squared. Now this is the vector form. All right, I want the magnitude. So to get the magnitude, we just do the square root of the sum of the squares. So let's do that. Let's get our square root, and then we're going to take each of these and square them, and then add them together. All right, there's technically a negative in there, but it goes away when you square. Okay, so now we have that. So that gives us 4,489.11 miles per hour squared. And this is the acceleration of b relative to a. Okay, so we're almost done. So that's the magnitude. Now let's go ahead and find the direction. So for the direction, we're going to use this vector. All right, so let's look here. So on this is the acceleration of b relative to a. So basically you would have car A here, and we're going to draw our vector from car A. So if we look, we have a positive x and negative y. So that means this appears to be our acceleration of b relative to a. And what I want to do is I want to find the angle this vector makes with the horizontal. So I want that theta. All right. Now I've got my components of this relative acceleration. If y'all remember from right here, I've got my x and I got my y. So with that, the x component is right here. That's the 2392.95. The y component is the 3798.15. I left off the negative because I know it's negative, I already drew it going down. We don't need to include the negative sign. So with that, then we can solve for theta, because essentially you could write a right triangle where that's theta. This side here is 2392.95, where this one over here is 3798.15. Okay, so now we have our triangle. Let's go ahead and find theta. All right, so theta then is going to be the arctangent of, we got opposite over adjacent, so 3798.15 over 2392.95. And then we need to find that angle. And once you put that in the calculator, you should get 57.8 degrees. All right. So that's how you go about doing that problem. And the key about that problem is just to remember when we have motion on a curved path, like we do with B, because it's on this curved road right here, you have to remember to look at the tangential component as well as the normal component. All right, you gotta have both of them and include both of those in your vector just like we did right here. Okay, all right, that's the end of that one. See y'all next time.